All right, so in this section, we are going to utilize example of CCM, non-ideal buck boost topology, to show you how can we utilize the state space averaging method to establish the DC model for the converter. So first, let's consider how to establish the DC model. So for the buck boost topology, we have two operation modes in CCM mode. So mode 1, we can plot its equivalent circuit. For here, non-ideality means that we consider the on-state resistance of MOSFET, and also we consider the on-state voltage drop for the diode. So for mode 1, the MOSFET is conducting, so we can plot its equivalent circuit accordingly. Here is the input source. Here is the MOSFET in on-state. We use a R-on to denote the channel resistance of the MOSFET. So this is the inductor. On the output port, we have the capacitor C to provide power to the load resistor R. And here is the output voltage, Vt. So based on this linear circuit, we can first denote its directions or polarity of the current and the voltage. So for example, the input, we care about the input current. This is IGT. And also we care about the inductor current. We denote this is as the positive direction as IT. Also we care about the capacitor current, ICT. And for the voltages, we care about the inductor voltage, VLT. Okay, so based on the equivalent circuit here, we can write the state equations and output equation. So for state equation, we consider the inductor current and the capacitor voltage as the state variables. We can list the two equations. One is the inductor current equation. For inductor current, we have inductance times derivative IL over dt equals to the input voltage minus the voltage drop across this R-on, which is the current times resistance based on Ohm's law. And for capacitor current, the capacitor voltage, right? We also have an equation, C times dV over dt equals to the capacitor current IC. Based on KCL, this quantity equals to the negative of this current minus V over R. And for this circuit, we denote the input current as the input vector. So we'll have the as the output vector, so we'll have Ig equals to inductor current in mode 1. So next, we can introduce the matrix to denote the state equation and the output equation. So in matrix format, so combining the first two, we can get the state equation. So we'll have derivative dt of the state vector, which is inductor current, capacitor voltage. So we extract the matrix here, so which will be a 2-to-2 matrix coefficient. So fill those numbers, so will be L0, 0, C. And on the right-hand side, we can do the similar thing. So there are two parts. First part is also the state vector part. We first place the state vector. Second part is the input vector part. For this non-ideal buck-boost topology, we consider there are two independent sources. One is the input source as Vg. The other is the voltage drop of the diode in on state. We consider this is Vd. So then we can fill those matrix of coefficients by just comparing them. For example, this one tells us that we can fill the first line will be minus on resistance 0, 1, 0. So which make it correspond to this equation. And the second line correspond to the second equation. We also fill those empties. So minus 1 over r, 0, 0. Okay, and also we can use the symbols to denote, right? So for this one, this will be k derivative x over dt equals to, this one is A matrix, A1 matrix, x plus, this one is B1 matrix times U. And next, we can process this equation, right? This equation. So this is very simple, but we also can use matrix to denote. Left-hand side is the vector Ig, output vector, equals to state vector parts plus input vector parts. Then fill the blanks. So here is 1, 0. Here is 0, 0. So you will see that this one matrix equation is essentially this one. And also introduce the symbols to denote. So y equals to C1 x plus E1 U. So C1 is this coefficient. E1 is this coefficient. So that's pretty much done for mode 1. Next, let's look at what happens in mode 2. So in mode 2, we can also plot the corresponding equivalent circuit for buck-boost topology. So in mode 2, we have the MOSFET turning off. This is the input source. So MOSFET is open. And this inductor current will continue to flow through the diode. So the diode is here, right? In on-state, the diode can be modeled by a voltage drop, so which is a DC constant voltage source whose value is ED. Usually for PIN diode, this is roughly 0.7 volt. For Schottky diode, it's like 0.4 volt. So filtering capacitor and load resistor. And this is the output voltage, which is also the capacitor voltage. And similarly, we mark those different quantities correspondingly. So here is the input current. And here is the inductor voltage. And this is the inductor current. And this is capacitor current, ICT. So similarly as what we did for mode 1, we can list those three state equations and output equations. So for inductor equation, we have L di over dt which is essentially the inductor voltage based on KVL in this loop. So this quantity equals to the difference between the output voltage and the diode voltage. Second equation for capacitor is C dV over dt equals to, based on KCL in this node, equals to the difference of this current and this current, which is minus V over R minus inductor current. And for the input current, since the MOSFET is off state, so the IG will be equal to 0. So till now, we have also obtained the 3 equations for mode 2. We can also express them in matrix form. Matrix form. So for the state equation matrix, d over dt, state vector, which is IV, the inductor current and the capacitor voltage. So we fill the blanks for the coefficient matrix by comparing those 2 equations, right? First equation gave us coefficient of first line, which is L0. Second is 0C. And this equals to the sum of 2 parts, state vector parts, and input vector parts. Then we fill those blanks of the coefficients matrix. So see, this gave us the first line of those 2 matrices. So fill in the blanks 0, 1, 0, minus 1, right? So it equals to V minus VD, which agree with the right-hand side of this equation. And similarly, we do the same thing for the second line of those 2 matrices. So here will be minus 1 over R. And here is 0, 0. So similarly, we can use the symbols to denote, right? So K, derivative of x over dt equals to A2 x plus B2 U. And next, we look at the output equation. So this one can also be expressed in matrix format. The input current equals to state vector parts plus input vector parts. Because the current is very simple, equals to 0. So it means that all those blanks are equals to 0. So for this one, we can use the symbol to represent. So output vector equals to C2 x plus E2 U. All right, so now let's try to combine them together by doing the average over the 2 operation modes. Since in this section we are considering the DC model, so first we look at the DC quantities of those coefficients matrix. First is the A average equals to D times A1 plus D prime times A2. A1 is here. A2 is here. So it's easy to calculate their average over one switching period. So which is a 2 by 2 matrix. So minus d r on d prime minus d prime minus 1 over r. And for b equals to d times b1 plus d prime times b2. So which is also a 2 by 2 matrix, because here is b1. Only one term is not equal to 0. Here is b2. Only one term is not equal to 0. So it's easy to calculate. So this 2 by 2 matrix is d minus d prime 0, 0. And next will be C. The average of C1 and C2. So C 1, 0, C1, 0, 0, C2. So the result will be only containing the first part, which is D0. And next will be E. Is the average of E1 plus D prime E2. So E is 0, 0, 0, 0. So the average is still 0, 0. So till now we have fully solved those four average coefficients matrix. And remember, we have obtained the DC model, two equations. So I will rewrite those two equations here. So it's like, first one is the state equation. 0 equals to A x plus B U. Second one is y equals to C x plus E U. This pair of matrix equation is what we derived in last section. So based on this group of equations, we can solve actually what's the value for x, right? Basically, you can see that you move this part to the left and then do the matrix calculation. You will see that the dcx will be equals to minus A inverse times B, right? So this A shift to the left will be A inverse. B is here, and U, the input vector. And Y equals to, we substitute X into here, right? So this will be minus C A inverse B U plus EU. So EU can be extracted. So we merge them together. This will be E U. So we can solve, basically can solve the DC value for X and Y. All right. And also, remember that for the U, right, U is the input vector equals to the independent sources, right? Input source and delta voltage drop, VD. So basically we can insert the value for A, calculate inverse, times B times U. Similarly, we can do the same thing to this equation to solve X and Y. So basically, you will see that X equals to a vector which includes the DC quantities for inductor current and the capacitor voltage. So equals to the A inverse, right? A inverse times B times the U. So basically, A inverse times B, we will see that it equals to 1 over 1 plus D over D prime square times R on over load resistance. And here is a 2 by 2 matrix, which is D over D prime square R. And here is 1 over D prime R. Here is minus D over D prime. Here is the 1. So this part essentially equals to this coefficient. Okay, coefficient. We have learned how to calculate in linear algebra. You can do it yourself after the lecture. So the U part will be as it is, right? So we consider, here we only consider the DC quantities. So we will have DC value for input voltage and the DC value for delta voltage drop. And for this one, we can do the similar thing. So equals to the DC quantity for the input current, the output vector, right? And also we can calculate the coefficient matrix by using the linear algebra knowledge. So this will be equals to same coefficient, 1 plus D over D prime times R on over R. But coefficient will, the matrix will be slightly different. So D square over D prime square R, 1 over D prime R times the input vector. If you look at those two DC models, right, you will see that this gives you the analytical expression to calculate the average inductor current, right, and also the output voltage and input current. So if you compare the results with what we derived in the previous chapter, by doing the DC modeling, you will see that they are essentially the same. Okay, but here we can use the standard state space and average method to solve it. Okay, now let's erase the blackboard. Okay, we have erased the blackboard. So in the last board, we have calculated the coefficients matrix like A1, A2, A, B, C, E, right? So in this board, we are going to learn how to do the small signal AC model. Of the non-ideal buck boost converter. Remember, when we generally describe the CCM PWM converters, we have derived the state space equations and also the output equations in matrix format after we're doing the linearization, right? So now let's rewrite those two linearized small signal matrix equations. Like we have the first one as K derivative state vector over time equals to average A state vector plus average B input vector plus A1 minus A2 x plus B1 minus B2, U, D cap. So that is the state equation, matrix equation, right? So in the previous page, we have derived A average, K average, and B average. But we still need to handle this one, right? Now let's calculate what is this coefficient matrix. So basically this equals to A1 minus A2 plus B1 minus B2 U. We just insert those matrix coefficients one by one and combining them together. So the first part is equal to a 2 to 1, 2 by 1 matrix minus V minus I R0 on I. The second one is equals to Vg plus Vd 0. So combining them together, we just add them correspondingly. So this equals to Vg minus V minus IR on plus Vd I. So next, we can insert this coefficient matrix to here. Meanwhile, we also insert A, B, and K to the above matrix equation. So we will have, here is L0, 0C, derivative over time of state vector, which is inductor current small signal, capacitor voltage small signal, equals to A, we have solved A equals to minus D R on D prime minus D prime minus 1 over R. And the state vector is I cap V cap plus B part, right? B we also have solved. B is D minus D prime 0, 0. And here is the input vector in small signal, right? So note here, for the input vector, we contains two parts. One is the input voltage source, one is the delta voltage drop. Generally, we consider the delta voltage drop, Vd, is a DC quantity. So when we consider its first order AC term, so it will be equal to 0. Okay. There is no small signal perturbations from the diode forward voltage drop. And also we have this part, right? Times small signal duty cycle. So that's for the state matrix equation. Next, let's look at the output matrix equation. So Y cap equals to C average X cap plus E U cap plus, this is C1 plus C2 minus C2 X plus E1 minus E2 U D cap. So we also are curious about this one, right? How to solve it. We just insert those C1, C2 E1, E2, and also X and U into it. So we can easily solve this expression. So basically, C1 minus C2 plus E1, E2 this equals to a one-to-one matrix SI. So next we insert C average, E average, and this combined together to this output equation. So we'll have left-hand side as the input voltage, input current small signal equals to C average equals to D0, and X small signal equals to I V, and E average equals to 0, 0, and U small signal VG cap 0. This part is I D. So those are the obtained results for state equation and output equation. Our target is based on those small signal AC equations. We want to derive the small signal equivalent circuit. So we can first convert those matrix equations into scalar format. So in scalar form, this one can be decoded into two equations. One is for inductor current, one is for capacitor voltage. So first is inductor current, L di over dt. So equals to d cap small signal V minus d R on times I T plus D times Vg, right? D times Vg T. And for the D terms is this one, right? Vg minus V minus R on plus Vd. Small signal duty cycle. That is the scalar form inductor current equation. And next, we look at the capacitor voltage equation. So C dV over dt, which is the second line of those matrix equation. So we just compare, right? Compare and write the scalar equation to here. You will see that there are minus d prime I minus 1 over R V, and here is 0, right? Here is I d cap. So three parts, minus d cap I minus V over R plus average current times small signal duty cycle. And the third one is this one, right? Just one scalar equation. Left-hand side is small signal input current equals to D times small signal inductor current plus this one, right? Average current times small signal duty cycle. the duty cycle is time varying. Okay. So here is the scalar form for those state equations and output equations. Next, we map those equations to the equivalent circuit, so we can do as what we did before. Right? Those scalar form equations are already the same results we have obtained in the previous methods, right? So next, we do the similar thing. So first, we look at this one. So based on this one, we can obtain the input port equivalent circuit, right? So this will be just a input source in AC. So here is VG cap. And this one can be modeled by a controlled current source. Whose value is D times I cap. I is the inductor current, which will be in the middle stage, right? So we use a control source. And this one can be modeled by an independent source, whose value is I D cap. D is the controlling signal, which is external, so we use independent source to denote it. And also we can mark, here is the input current, IG cap. Next, we look at the middle stage, which is the inductor equation. So we can see that we have the input port part here. So this can be modeled by a controlled voltage source. As D times input small signal voltage. And this one is still a inductor behavior. And here is a resistance behavior. The resistance, it will be D times R on for MOSFET. And here will be another independent source, right? Which is controlled externally. So this independent source value is VG minus V minus I R on plus VD times D cap. And then we still have this one, right? This one is another control source. Controlling signal is the output voltage. So we use a controlled source here to represent. So here is positive, negative. We close loop. Then this quantity will be equals to D prime V cap. So it's done for the middle stage. Then we use this third equation, the second equation to establish the equivalent circuit model for the output stage. So basically, this part will be a controlled current source, right? The controlling coefficient is D prime. Controlling variable is inductor current, right? Inductor current. So this, basically this current is inductor current. And we have this item will be a resistor behavior, whose resistance is R. And the output voltage here is small signal V, right? Small signal V. And next, we look at this one. This one will be an independent current source, controlling by duty cycle externally, right? So we use a current source here as I D cap. And we also have the C dt part. This is a capacitor behavior whose capacitance equals to C. So we keep the filtering cap here as it is. Now let's look at the obtained full equivalent circuit for the entire system. We see that there are two pairs of control sources. This pair is a pair of current source and a voltage source. They have the same controlling coefficient as like D, right? Here, similarly, same controlling coefficient as D prime, right? D prime. So our previous knowledge tells us that we can model them by AC equivalent transformer, right? So we can establish the transformer-based AC model for the buck boost converter. Okay. So now let's plot the modified results. So here we use a transformer. The transformer has the same coupling points on top side. We use a wave line to show that this is an AC transformer. And the turns ratio for this one equals to 1 to D, as the controlling coefficient shows here, right? And then we have the inductor current I, inductor, resistor. So here is L, DR. Independent source, D, small signal. And another transformer, right? This time, note that the polarity is inverted here, so the coupling point should also be inverted. So meaning that we have coupling point in output side to be downside, right? So this also wave line shows that this is a AC transformer. The turns ratio for this one will be equals to D prime to 1. So here is the independent source, filtering capacitor C, load resistor R. Till now, we have fully derived the transformer-based linearized small signal AC model for non-ideal buck boost converter utilizing the SSA method. Okay, so in this section, we used the state space average method to build the AC small signal model for the non-ideal buck boost converter. So as what we can see in the blackboard, the derived equivalent circuit model is essentially the same as what we have derived based on the previous learned method.